Hello everyone, my name is Gabriele Baldoni and today I will present our last work, which is facilitating distributed data flow programming with Eclipse Zenoh, the ERDOS case. I want to thank also the co-authors, Julien Lode, Luca Cominardi, Angelo Corsaro, and Yong He. So let's start with some introduction. In the recent year, we have seen the emerging of edge computing. What is edge computing? Edge computing is about distributing all the computing networking and storage fabric across the edge to cloud continuum, which means that you don't have only powerful servers and storages and networking on the cloud, but you have also the possibility to have this computing networking and storage fabric closer to the user, which means either inside the operator network or also on premises or closer to the user premises, like in case of robots, autonomous vehicle, or industrial application. In cloud, you have seen the emerging also of the function as a service paradigm. The function as a service paradigm is about decomposing your application on very simple components, also known as function. Those components can communicate with each other, or you can compose a very complex application by just interconnecting simple functions. Then those simple functions, of course, have different life cycle. For each of those functions, you have a different life cycle. In particular, in the function as a service paradigm, you have the possibility to run this function as a service, which means you pay only when you are using this function. That function is provided with an endpoint, so you can reach that function from, let's say, whatever on the internet, and you can really pay only when you are using the function. There is also another paradigm which resembles function as a service. It's a paradigm that is not really new. It was used for a lot of years in especially aerospace and the military applications, but now is emerging also for consumer application, especially for robotics and autonomous vehicles. Is the data flow programming paradigm. In data flow programming paradigm, you have operators, which we can see as function because their goal is just to compute some, based on some to provide some outputs, so to compute something. And those operators can be of course, they are, let's say, agnostic of the application they're running it, and you can compose different applications depending on the way you create a graph of this operator. This operator exchange messages that are strongly typed, and the data flow application itself, as I said, is composed by a graph of these operators. Different application, of course, requires different graph, but the same operators can be present on different application. This is similar to what you have in functional serving, in which you have different function that you can use to compose different application. And so you can use function, and as said, in data flow, you can use operators. Of course, in the data flow paradigm, there are some special kind of let's say, operators, although they are not operators, which are the source and the sink of the graph that in this picture are named input and output. And as we can see, we have different components of those graphs. We have data, we have links that in theory are unbounded FIFOs, and then the port between the links and two different operators, in this called ports. And then we have of course, we can have loops, we can have data that flows. Now let's take a look at some background research we have done for our paper. Let's start with ERDOS. ERDOS is a data flow framework from autonomous vehicle, which is coming from UC Berkeley. It's quite used and it's quite powerful. They use that for the autonomous driving simulator, which is called Pilot, which has won the Carla Autonomous Driving Challenge, which means that is what they were able with ERDOS and this pilot simulator to achieve a good level of autonomous driving. So ERDOS, as say, is a data flow framework, which means that we have operators that are connected via data streams, and those operators exchange messages. Those operators are agnostic of the application in which they are running, so it means that you can have the same operator on different application, and the application is composed by a graph. Different graph compose different application, of course. We have also, in this case, a separation between communication and computing, which matches the functional service paradigm, because as said, operators focuses on computing some data and producing some result, and then they just handle this message to the framework that will send the message to the correct operator to continue the execution of the application. So the communication portion is done by the framework, while the computing is really user code because it's the function or the operators. On the other hand, we have this interesting project, which is Eclipse Zenoh. Eclipse Zenoh is a named data networking protocol which provides unification for data in motion, data use, and data rest, and also computation. It means that it blends pub/sub, query request response, and also possibility to have RPCs. And it does that in a time efficiency in time and space. So it provides location transparency, it provides low overhead on networks, it provides the possibility to leverage on different transport, and it also has the possibility to work both on peer-to-peer on routered networks, which means that, as we can see in this picture, you can have a different topologies of Zenoh router interconnected that can communicate each other, and then they will throw the messages. So you can have like on-demand pools, you can have pub/sub, or you can have distributed queries. Like in this case, we can see the yellow line, it's a pub/sub law. So we have the customized device that is publishing some data that can end up in some storages or deleting some device, while we have the dashed yellow line, which is a distributed query. So we have a device that is asking for some data that we will be able to recover from the storages. And we can also have like devices that are asleep. So as we can see from the orange line, we have a sensor that is publishing data that is getting closer to the subscriber for those data, but the subscriber of that data is sleeping, so it will receive the data once it come back. And then, of course, Zenoh is very powerful because it also provides built-in support for geo-distributed storage and geo-distributed computation, which means that you can interconnect what now they are called data lakes through Zenoh, or you can have distributed RPC through Zenoh, which is crucial also in the case of function as a service. So we had these two components out there in the, let's say, in the state of the art, and we thought, okay, what happens if we integrate them? Because we see that ERDOS is a quite good data flow programming framework, but it is designed to work on a single machine for the time being, while we have Zenoh, which is this named data networking protocol that can augment quite a lot the capability of the ERDOS. So first, let's have a look at the current ERDOS implementation. The current ERDOS implementation is depicted in the picture that we can see in this slide. So we have separation between data and control messages. Then we have this ERDOS node. And on top of the ERDOS node, we have the ERDOS API and then the operators. The ERDOS node is a component in which you can run one or more operators. In the current ERDOS implementation, and for the time being, you can run, each node will run just one operator and run as a process in a single machine. So you have each operator will run in a different process, and we need to have some communication between those operators. The communication of those operators is leveraged on TCP sockets, both for data and control messages, which means that you have sockets for data and sockets for controls. And in order to achieve communication between all the operators in the graph, what ERDOS does is a full mesh connectivity. So if you have like 20 operators in your graph, you will have a full mesh network of 20 nodes, which means that you will have 2 times n-1 TCP connection with n number of nodes. We have 2 times n-1 because we have a separation, as said, between control stream and data stream. Control stream are used to see if all the operators are there and if we can start sending messages, while data stream are just data streams. Of course, the messages are not broadcasted to all the operators, apart from some of control messages, but data message will just flow on the TCP connection between the 2 operators that are interested in that communication. So if I'm sending a message downstream to an operator, I will use the TCP socket that connects myself to that operator. When it comes to integrating Zenoh, we see that we can already get some interesting properties like location transparency, which means that, as already said, Zenoh is a NDN protocol. We don't have notion of, let's say, IP address, but we have a notion of only naming the data. So if I need to communicate with an operator, I need just to know its name. I don't need to know where that operator resides, so I don't need to know its address, which means that that operator can also migrate, can be moved across the infrastructure. As long as I'm able to reach to have Zenoh connectivity, I will be able to communicate with that operator. This introduces also some decoupling between the underlying networking infrastructure and the data flow graph, because there is not this one-to-one mapping between them, but we leverage Zenoh that manages all the underlying networking, and then we have our data flow graph based on subscription and publications. We also reduce the footprint because we can have fewer TCP connections, and also we gain on transport independency because I said Zenoh can run on different transport. In particular, we can run on TCP, UDP, QUIC, and also Unix sockets with support for DTLS for TCP, if I'm not wrong. And so we gain also the possibility to use different transport. So that means that we can also do some of the overhead of the network if, for instance, we want to use UDP for some messages. As we can see, we have replaced some components in the ERDOS architecture. In particular, we don't have any more the TCP stream, but we have some serialization, deserialization fabric as usual, and we have a couple of publisher and subscribers, and then we have a Zenoh session. And Zenoh will manage all the connection with the other nodes or operators. So in this picture, we can really see what are the difference between the two architecture. So we have seen that we replaced all the TCP stream, the frame, and the sync and the stream components with a couple of pub sub and a Zenoh session. And we can see that while in plain ERDOS, we have ERDOS connectivity that is done to each operator of creating a full mesh. Using Zenoh, you can leverage on routing or on peer-to-peer to have less, to achieve a better scalability, which means that you can have operator that runs, let's say, in the same local area network that they can run on a peer-to-peer fashion, but you can have also a router on that network. So you can communicate also with operators that are not on that network, which means in that case, you don't need to have a full mesh connectivity, but Zenoh will connect directly through the Zenoh router that will route the data to the correct operator. This introduces an interesting use case. As said, we have location transparency, which means that if you want to move an operator, it becomes quite simpler. We can see in this picture the different steps that you have when you migrate an operator in plain ERDOS, or when you migrate an operator in ERDOS plus Zenoh. So when we migrate an operator in ERDOS plus Zenoh, we first need, of course, in the both case, to trigger the migration process. Then we need to discover some IP of the infrastructure because we need to know where the operator was migrated. We may need to do some configuration of the infrastructure networking because, for instance, we are in a data center, we need to do some OpenFlow or some configuration on the switches in order to achieve connectivity between these two machines. Then we need to create the TCP link, provide some state alignment, and then we can have the data flows. While when we want to migrate an operator using ERDOS plus Zenoh, the situation becomes far simpler. We trigger, of course, the migration process. Once the migration is done, we can just have a new subscription, and then the data will flow. The state alignment comes for free in Zenoh because I said we have distributed storages, so we have the possibility to checkpoint regularly the state of the operator and recover it directly when we are migrating. And of course, that is also transparent for the operator itself because everything in Zenoh is named data, which means that the operator will describe its state with a name and will be able to recover its state independently for where the operator is residing and where the state is residing. So we have done quite some modification to the underlying layers of ERDOS. We now check if that modification has some impact on the performance. In particular, we are interested in throughput and latency measurements. So let's start with throughput. We used the same pipeline for both implementation, which was composed by a source sending data as fast as possible and the receiver receiving data and counting from the messages that it was receiving. And we have done this in a transparent manner for the user, so all the underlying modification can be enabled or disabled by the user, so the user can use the same code to use Zenoh-based ERDOS or a classical ERDOS, let's say. And as we can see, we have run the different runs for different payload size, starting from 8 bytes to 4 meg. So we can see that we almost double more than double actually, the performance of the ERDOS TCP implementation. This is easy to understand if we keep in mind that as Zenoh has control on the TCP socket, it can also do some batching, which means that for small messages, we can really a lot increase the throughput, and we can really leverage at maximum the underlying TCP connection. For this case, which is the case of a throughput test, in which we are sending messages as fast as possible. then we can see that starting from around 256K, the lines are similar because this is like the limit of the Zenoh batching. So in this case, we are sending one message for each call to the sockets, let's say. And so we can see that the performance is quite simple. Also, we can already see that the variance is very, very low when sending messages using Zenoh ERDOS that when using TCP. This also can be explained by the fact that we are leveraging and we are using at maximum the TCP windows and the TCP sockets. Of course, we have another layer now on top of TCP, which means that we have a little bit more latency. As we can see on this graph for the round trip time, the tests is quite similar. In this case, we have a different chain of operators with that in which we are able to get the timestamp between the sending messages in our ping pong function. So we send the message, and when we receive the pong, we have the RTT from the other operators. Of course, the RTT is a little bit higher when using ERDOS with Zenoh, of course, because we are adding a layer, and on top of that layer, we are also doing some batching. So but we can see that the introduction of this, the introduced latency is not that much, is around 10% more or less. And also the variance is quite small, which means that we are still able to have bounded latency, although we can also have distribution. Of course, all these tests are running on the same machine DOS. There is no networking, not really networking involved. So what are the conclusions? The conclusions are that we have seen that data flow programming can fit in the function as a service paradigm because we have the same concept of the composition of application on simple tasks that can be either function or operators, and these function operators can ideally be run on different portions of the infrastructure. We just need to interconnect them. But however, current data flow frameworks are not fit for the edge to cloud continuum because they are mostly designed for a monolithic deployment. Like ERDOS works very well when the current ERDOS implementation without Zenoh works very well if you deploy your autonomous driving application in a huge server or in your machine. But if you want to move some of the components outside of those server, like some perception done at the edge, or different components running at the edge, and some components running on the cloud, some components on the car, that can be quite complicated with the current data frameworks. So ERDOS has said it can fit also the functional service paradigm with some tweaks, and we have seen that with some tweaks, like introducing the possibility to use Zenoh data transport, we first facilitate the connectivity management, and also we can see that we can increase in throughput despite adding a small increasing in latency, and we also introduce location transparency and distribution that is quite useful in this domain. What we plan as future works, we plan to enable end-to-end function as a service application in the edge to cloud continuum. This includes time-critical applications like robotics, automobile, or industrial control. The goal that we want to achieve with our future works is to provide a single API for the users to create their own data flow or function as a service application that is able to run on different machines, ranging from the cloud to the edge to small robots or the car directly. So the plan is to design a data flow framework directly based on Zenoh, which will also integrate more function as a service concepts. So thank you very much. And I want also to thanks again all the co-authors, Julian Lodè, Luca Cominardi, Angelo Corsaro, and Yonke.